Hmm. Okay, it's about time. Can you all hear me okay? Okay, good. If you want to turn on your cameras, great. If not, I understand. Kind of helps me. So I just sent everybody a notification. It has, I think, 5 files that are waveguide.pdf. It might take a second to get there. There are a bunch of different PDF files that were created some time ago that we kind of use at times to discuss waveguides. Now, typically what I do if I'm in person with you, I'll bring down a waveguide and show a person what they look like. Oh, before I continue with this. So I still have a little bit of congestion and I feel occasionally it's kind of weird, chills, a little bit of sweating and chills. And I'm not sure why, but I guess it's just a residual, but I'm pretty much over all the stuff. I'm not contagious. So I plan on meeting all next week and from here on out in person. Get that out of the way in case anybody's wondering. We'll take care of the quiz. We'll have a quiz the following Friday. I mean, this coming up, not today, but next Friday, we'll have a quiz based on the materials. And I'll try to be as clear as I can about this. It'll probably be on either oblique incidence waveguides or some combination, but I'll be very clear about. Let me first, can anybody confirm that you received that email with the PowerPoints and some PDFs, some PowerPoint? You got it? Logan, you get it too? Okay, all right, good. So I don't know where the music's coming from, but if I can find it, I'll mute it. Anyway, what I want to talk to you now today about is, do you first have any questions about the material we covered with oblique incidence, any of the problems, any questions at all? If you do, now's a good time to ask, and I'll try to answer them. Well, I got to share a screen too. I think that's that one. So you should be seeing a piece of paper. So everybody can see this yellow paper with my hand? Okay, good. All right, so any questions at all about the homework, anything like that? Well, I try to arrange this. Every time I do something like share, it rearranges how you guys look, and I have to stretch everything to see if there's hands or questions. And there is a chat in case you want to put a question in chat, and you all should be able to unmute yourself, I think. All right.
Can we do 6.5?
6.5? 6.5? Yeah, okay, sure. Let me get it. That's going back some, but you can. So I assume you're talking about this problem right here.
Sorry, 6.50.
Wrong one. Okay. All right. So if you don't have your book, I hope, can you all read what I've got here? Can you see it okay? All right. So it says a randomly polarized, uniformly polarized wave at 200 megahertz is incident at the Brewster's angle from air onto a thick slab of lossless non-magnetic material with epsilon relative 16. The wave can be decomposed into TE and TM parts, each with an incident electric field amplitude of 10 volts. Find the expressions for the instantaneous incident reflected field, reflected and transmitted electric fields. Okay. The big thing that's this one is I'm going to talk my way for a second, then we'll do it. They give you the material epsilon relative equals 16, right? Follow me on that? It's air and then epsilon relative 16. So the wave is incident at the Brewster angle. It means all of the TM polarization is going to penetrate. There's no reflection. You all follow me? That's the whole deal with Brewster's angle. So if you look over here, this is how we find out what Brewster's angle is. Oops. If you look at equation 6.147, that's how you figure out what the Brewster angle is. Do y'all follow me? All right, now that's the key. We're going to get this in 1 second. And once we get the Brewster angle, then we can go ahead and write the expressions in the phasor and in the actual, does he want? So he wants the instantaneous values for TE and TM for both reflected, incident, and transmitted. Okay, we can do that without a problem. Now, here's the deal. That angle right there, the Brewster angle, is the angle in the first media that the wave is going to strike it to with respect to the normal. I got to find a way to turn this bell off. Hold on. Every time somebody comes in here. Oh, maybe I can't. That's all right. I'm not sure where that sound's coming from. Anyway, we'll keep working on it. Y'all follow me on this one? You asked about Jake. You follow me? All right, so here. Starting to get to me. Oh, give me 1 second. Let's see. There's got to be a way to shut that thing down. All right. I hope that killed it. All right. I'm going to go here. I'm going to do this on MathCAD in a second. So epsilon relative 1 is just 1 because it's air. Epsilon relative 2 is 16, correct? Isn't that what the problem states? All right, so we're going to get square root of 1 over 1 plus 1/16, or really this is going to be 17/16, 1 over that. You all follow me on this, class? So I'll just put this down here. To get the Brewster's angle first, I know that the sine of the Brewster's angle is equal to the square root of 1 over 1 plus epsilon relative 1 over epsilon relative 2. In my case, that's equal to the square root of 1 over 1 plus, here epsilon relative is 1, epsilon relative 2, I believe was 16. You correct me if I'm wrong on that. And that means this is going to be the square root of, that's 16/16 plus 1/16 is 17/16, or this is going to be 16/17 is the sine of the Brewster angle, or the Brewster angle is just a sine of the square root of 16 over 17. And I'll do that right now. Right here. $75.964 degrees. Is that what you guys got? Did you do, is that what the answer is, Jake, or I don't know? Y'all follow me what I did there, guys? Or not? I'm the only thing I did is this. I went ahead, sorry. I just solved this. That's it. So that's the Brewster's angle. He gave us, that was the incident angle. It was at the Brewster's angle, right? So if it's coming in at that angle, we'll do the TE polarization. Or yeah, we'll do TE first. So for TE, you have to actually assume something here. This is going to be Z, this is X, and Y is out of the board. So if this is a TE polarized wave, we're coming in at this angle. That's the Brewster angle, right? And that was, what was it, 75 degrees or something like that? But we just calculate the Brewster angle right there. Now the electric field for the TE mode incident in the phasor domain, they gave us that it was 10 volts, right? As the magnitude. And then it's going to be e to the minus j beta in region 1. I'll talk about that in 1 second. And then this is going to be times x times the sine of the incident angle. That's the sine of the Brewster angle, plus z times the cosine of the Brewster angle, because that's the angle it was given that was coming in at. And it's in the AY direction. Do y'all agree with that? Can y'all follow me while I'm doing it? All right. So what else they give you about this problem before I want to get beta on this one. So they give us 200 megahertz. Now pay attention to this part. So I have 200 megahertz as the frequency, right? If I want beta 1, how do I get beta 1? Anyone? You can unmute. Anybody? Eli, did you say something? Well, when we know,
Sorry, I didn't realize that.
all right, beta, it's lossless. Do you all agree if it's air, it's lossless, right? Therefore, beta in general, beta in air or in a lossless media is just omega square root of mu epsilon, right? Well, if it's air, it's just omega times square root of mu naught epsilon naught, or really it's just what, omega over c, isn't it, class? And therefore, I can say that beta in region 1 would be equal to omega or 2 pi times, and this is just 2 times 10 to the 8th. And it's over 3 times 10 to the 8th, right? And that means beta in region 1 is equal to, and here, 10 to the 8ths cancel, right? And you get 4 pi over 3. And that would be radians per meter. That would be beta in region 1. All right, while we're at it, how do I get beta in region 2? Same way, exactly, right? Except one thing. Now, beta in region 2 is still going to be omega times square root of mu epsilon, right? But now it's going to be omega times square root of mu naught epsilon naught times square root of mu relative epsilon relative, which is really square root of 16. So that means it's omega over the square root of mu naught epsilon naught, or it's beta in region 1, which is, so it's really this, that is beta in region 1. and its square root of 16 is 4. So that means beta in region 2 is just equal to 4 times that, or it's 16 times pi over 3 radians per meter. All right, everybody follow me on that? Now, next thing we do, and let me get this back here. So that was the incident angle, right? They said it was at the Brewster angle. That's what it is, right? How do I get the transmitted angle, guys? Anyone? This is always an interesting. Everybody's muted. Nobody wants to talk. All right. Well, what law do we use? Begins with an S.
Snell's law.
Snell's law. That's right. Snell's law says what? Beta in region 1 times the sine of the incident angle is equal to beta in region 2 times sine of the transmitted angle, or call it T. Well, we already know what this is going to end up with. Beta in region 1 is 1/4 beta in region 2, but I'm going to just write them down there. We know that this is going to be equal to omega times square root of mu naught epsilon naught times the sine of the incident angle is equal to omega times square root of mu naught epsilon naught times square root of mu relative epsilon relative in region 2 times sine of the transmitted angle. We can see a whole bunch of this stuff cancels. And really, I have just the square root of epsilon relative, and in region 2, epsilon relative 16, so that's 4. So if I take the sine of the incident angle divided by 4, that is the sine of the transmitted angle, or we can get the transmitted angle here is equal to A times the sine of the incident angle over 4. And that means the transmitted angle, if I come back over here, might as well do the whole thing. So I'll just do it this way. Theta transmitted is equal to A times the sine of the sine. There's a shortcut for this, but I'm not going to do it. 75.96. Or I'll just call it sine of so I'm getting 14.036 degrees. Can anybody confirm that? I don't have my solutions up. Is that right? No? That's the angle. It has to be. All right, that's the transmitted angle. Do you all agree with that? It has to be. All right, that's simple Snell's law. So the transmitted angle is going to be 14. By the way, you can see that screen over there, right? That I'm casting. Okay, good. So now getting back to this, that's 14.036 degrees. And the incident, or the Brewster's angle is 75.964. And now the E field for the TE mode. I want to do it this way. This is going to be the E field transmitted for the TE mode. So, what do we have to do? We have to get the transmission or the transmission coefficient. And we need the reflection coefficient for the TE modes, right? And do you remember that the reflection coefficient was eta2 minus eta1? We know it's going to have that form, right? Here it's going to be cosine of theta incident. This is going to be cosine of theta transmitted. And it's over the sum eta2 cosine theta incident plus eta1 cosine theta transmitted. Do y'all remember this is the reflection transmission? Well, this is the reflection coefficient. The transmission coefficient for the TE mode is just going to be equal to 1 plus the reflection coefficient for the TE mode. So this is the key thing. We might as well get this next, and I'm going to do that using MathCAD. I don't mean to spend so much time in this, but it's kind of good to go through one problem entirely. That way, the questions you have or that you don't know you have at least will come out and be answered hopefully. So when I come here, now first I have to say that eta naught is equal to just 120 pi. And then after that, I'm going to say that eta in region 2, or the transmitted field, that's equal to eta naught, right? And it's over the square root of 16, or really over 4. Oh, sorry. Do y'all know what I'm doing here? It's technically a square root of mu over epsilon, but square root of mu naught over epsilon naught is just 120 pi over the square root of epsilon relative, which is 16, the square root of that is 4. So that would be the 2. Do you all agree with that? Next, I'm going to go ahead and I set up what the reflection coefficient is. This is for the TE mode. I just call TE. And that's going to be equal to eta 2 times cosine of the incident angle, theta BA. Matter of fact, I'm going to do something. I'll call it that way. Minus eta naught times cosine of theta t and so I'm getting a transmission coefficient or a reflection coefficient of minus 0.882. Is that what Whitworth had? Do you know? Anybody? All right, I got a question. How many tried that one? Jake, did you try that one? All right, is that what he has for the reflection coefficient or not?
Yeah, it's pretty close.
Well, I mean, how close?
It's within like it's how Wentworth rounds. That's it.
All right. Now that means the transmission coefficient is what? Well, I'll just call it tau. That's just 1 plus that, right? So I'm getting that. So now we have the reflection transmission coefficient. So now the only thing we have to do to get all the fields, and these are going to be phasor fields. If we went and we got the for the TE mode, we know the incident field here in the phasor domain would be equal to 10 times e to the minus j beta in region 1. I'll leave it as that, and then it's just going to be x times the sine of theta incident, or BA, whatever you want to call it, plus z cosine theta incident, or call it theta incident, doesn't matter, and the AY direction. That's the incident. The reflected field is going to be that reflection coefficient we just calculated. That would be the TE mode 1 times 10. Then it's going to be e to the minus j beta 1. The x sine theta of this is going to remain the same. So it's going to be x times the sine of the actual incident angle, or BA in this case, because it is the Brewster angle. But then it's going to be minus z times the cosine of the incident angle. Now, the incident and reflected angle are the same. So you can leave that as theta incident. And that would be in the, this is in the AY direction, this will be in the AY direction. And the transmitted actual value for the TE mode is going to be the transmission coefficient times 10. And here it's going to be e to the minus j. This is going to be beta 2. And this will be x times the sine of theta transmitted. And it's going to be plus z cosine of theta transmitted here in the AY direction. Now, I didn't go ahead and multiply these two together, but you can see since the reflection coefficient was about minus 0.882, this is really going to be minus 8.82 roughly volts per meter here. And this, the transmission coefficient, I think was something like 1.18. So this is going to be 1.18 volts right here times e to the minus j beta 2 times all this in the AY direction. Now that's the phasor form. Do you all agree with this, class? I'm just doing it for the TE mode. To take it into the time domain, the only thing you're going to do is you're going to take this term and you're going to multiply it by cosine of omega t minus, like for the transient, minus beta 2 times x, and it's going to be sine of that angle. And then it's going to be minus beta 2 z times the cosine of that angle. Do you all follow me? All right, that's it. That's it. When we do the TM case, it's exactly the same thing. What's the one thing that's different with the TM case? Because we are at the Brewster angle. What do we know the reflected field will be for the TM case? Because we're at the Brewster angle. Anyone? Does anybody know?
0?
Has to be 0. That's the definition of the Brewster angle, right? Everything's transmitted. There's no reflection, only for the TM case. So that's the definition of the Brewster angle. So in Wentworth's book, he should have the reflected field for the TM case being 0. Does he? I hope he does. Okay, good. I feel better about the book. All right, that's really it in a nutshell. Do you want me to work everything on this one, or is that you follow me on that one? All right, it just comes down to writing. You can write them in this. We just did the TE, the TM case is even easier. There's no reflected field, but you have to go through the math, and that's you just got to do it. That's the only way it works. Okay, now, any questions from anybody that's watching? If a question comes up and I miss it, just yell at me, all right? So today, we're moving into waveguides. And I want to tell you something about waveguides. Unlike transmission lines, they don't have a TEM mode, meaning when I say a TEM mode, normally when you have plane waves, like propagating here out in the atmosphere, this was the E field, E and H are perpendicular to each other and perpendicular to the direction of propagation. Both E and H are transverse to the propagation direction. They're transverse electric and transverse magnetic. Do you all follow me on that? That's a simple fact. Now, in a waveguide, what happens is, and by the way, in a transmission line where you have a coax cable, that will be true. Both the E field and the magnetic field will be perpendicular to the direction that the electromagnetic energy and field is propagating. But in a waveguide, it's different. A waveguide is basically a hollow pipe, and the waves bounce off the ceiling at a different angle. And you can have either TE or TM modes. Now I'm going to show you a picture of this waveguide if I can, and then go from there. I emailed it to you. I'm going to start right here. This is the best I can do. I can draw it here, but I think this might be a little easier. By the way, is campus jammed right now with cars and stuff? I mean, I'm assuming half a lot of people, the RVs and stuff are there. I haven't been up there, but I'm just guessing. All right, so I guess I could do the PowerPoint mode. I sent you all these slides, everybody. Now, when you talk about waveguides, the only thing they are tubes with constant cross-section dimensions. The cross-section doesn't change. They can be rectangular metal. That's the most common one. It's the rectangular metal guide, and the waves just bounce around in the inside of this thing. And I'll show you that later. You can also have a circular waveguide. Circular waveguides are useful for some applications. We don't cover circular waveguide solutions in this class. I wish we would, but it was Dr. Wentworth's option to not have them. I may if I have enough time to go through them because it's kind of unique. The solutions of these are not sines and cosines and stuff like that. They're Bessel functions, which I don't think any of you have had Bessel functions yet. You'll get it in communications, but it's important to at least touch on it before you graduate as electrical and computer engineers. There are also dielectric waveguides. They're just made of a dielectric. Now, the one thing about this is whenever you have a material that has a different permittivity or really constitutive parameters than the surrounding material, it will tend to cause the waves to stick to the surfaces and they'll bounce around inside here. I'll get to that later. It's different than the metal one where it just all reflects off, but it is interesting. Finally, the one that's probably of most interest to a lot of you for the long run are going to be fiber optic guides, because fiber optics, I mean, in a nutshell, can anybody tell me why fiber optics are so very important? There's a couple reasons, but well, one is fiber optics carry an enormous amount of information. They can use really lasers, optical lasers, to send packets of light. They're not modulating any kind of an RF frequency. They're just sending out little bursts of light. Think of them as ones and zeros. And they have an immense amount of data that they can put through there. Sometimes they refer to it as bandwidth and information theory, but the amount of data you can get down a fiber optic line, a single mode fiber, is phenomenal. And they had eminent domain. They cut up my front lawn a while ago and they put in fiber optic cable. And this was Spectrum, I believe, that did it, but it's fine with me. The amount of information they can get on that thing is so much greater than any kind of coax cabling. It's not even worth talking about. Also with fiber optics, they are immune to EMI, basically. Now, the electromagnetic interference and compatibility. Lightning can occur. You can have any kind of transit wave. It's not going to affect these things unless the thing melts or something like that. It's basically immune. Now, fiber optics are really glass. They have a pliable type of glass made by DuPont or Dow Corning. And I'm not an expert on this. And what the fiber optic cable will have is an inner core. You see how it's epsilon relative to, I don't know, can you all see that okay right there? I gave you these things so you can open them up. That core has a dielectric constant just slightly bigger than epsilon relative 1, but it will cause the actual wave to bang around on the inside and stay there, and it will not lose any appreciable amount of energy. Now, fiber optics, that's another thing, that they lose very little in attenuation per kilometer. You can run fiber optics miles and miles, probably over 10 kilometers before you need what's called a repeater, where you have to take the signal and go ahead, parse it up into ones and zeros, and then retransmit it. They're phenomenal as far as reducing the loss. It's much smaller and lighter. The downside is they are expensive. And when you break one to reconnect it is no small task. It's not like just, with coax cable. If you cut a piece of coax, you can basically trim it down and put a connector on it and then connect it to the other side with a connector on, and you're fine. You don't have much loss there. You can't do that with fiber. Fiber is something where that's real glass there, and it has to be fused, and there's more to that than meets the eye. And I'm not a material science person per se. I have had crystal chemistry and graduate stuff in material science and some of the other stuff, but when you're getting into this type of stuff, this is really something that is beyond what I can talk about, I guess, effectively with at least surety. I'm not certain about a lot of that stuff because I don't work in that area. Okay, now with these guides, we're going to start with the rectangular one. And again, the one thing about the guide, waveguide, is it's got to have a constant cross-sectional area. You can't have something where you get a rectangle and it starts flaring outward and getting larger and larger like a horn antenna. It has to maintain a constant cross section, or we can't solve any problem. That's important. Another thing about this is, let me just move back for 1 second because you should know this. With these guides, you can put a little juncture, or you can bend them. You can't bend them very much. And there's what's called the maximum rate of curvature, because if you exceed that, then the wave that's going down there will reflect back. It will not keep going. So there's all sorts of limitations on the amounts of bends you can do and other things. And we'll get into that. And I'll try to get into it as much as I can without making it kind of trivial, where I'm getting into the weeds and you really can't appreciate what I'm talking about. So back to this thing. Now, I'm going to start there, and I'm not going to do it with this PowerPoint because I'm going to do it here. But what I'm going to do is show you in your book where it is, and then try to at least give you an appreciation for it. So this is Dr. Wentworth's book. And here's where he shows you basically what we just looked at. Now, what Dr. Wentworth's book does, he doesn't bother solving Maxwell's equations at first. What he does is just start talking about the guide and what happens in the guide. He doesn't solve the equations. I don't like that approach because personally, I think you should start with the basics with Maxwell's equations, solve them, and then talk about what the actual solution means in terms of propagation and modes. So that's what I'm going to do. Now, before I do it, I got to get over here and talk to you about some of this stuff so you have an appreciation for it. When we have a waveguide and we look at it, we know it's a square, really, they call it plumbing sometimes. It's a square tube. But one way you can actually talk about it intelligently, and mathematically it's accurate. If you superimpose two waves, a plane wave going this way and a plane wave going this way, and you allow the plane waves to have absolutely, the net effect of the electric fields will be, the tangent values would be 0 on this surface and this surface, then you would mathematically describe what's going on in there. To be really frank about it, what's going on with the individual photons, they're banging off the top and the bottom at some angle, and the net actual velocity of the wave is in this direction. It's down the guide, or in the Z direction. Y'all follow me on that? Just appreciate that. Now, if it's banging down there, if you think about it, and I wish I was in class with you guys, say my pen is the electric field. If the electric field is sticking out here and it's banging like this, try to understand this. Well, the electric field doesn't have a component in the direction of propagation, so it is TE, or transverse to the direction of propagation of the energy. Does that make sense to everybody? All right, now the electric field could also be in this direction, and then you could see it would have a component of the electric field in the direction of propagation. So what we do, just like we did when we talked about oblique incidence, if we have a mode that is TE, where the electric field is transverse to the direction of propagation, we analyze it differently than if we have an electric field or really a magnetic field that is transverse. The electric field would be in, now it would have a component in the direction of propagation. Can you appreciate that simple fact? All right. The way we actually partition this stuff and do the analysis is we say we look at the waveguide and we're going to analyze it as either supporting a TE or a TM mode. And depending on what mode we're assuming exists, we'll get different solutions. Does this make sense? You just got to realize from Maxwell's equations, you got to start somewhere. We've got to sort of limit the number of possible solutions. So now, in Wentworth's book, okay. So he starts with the TM mode. And now that's where I'm going to start here. And this is on page 388. So we're going to talk about the TM mode as best I can. And this is for a rectangular waveguide. It's just a rectangular guide as such. So I make this dimension A, it's the horizontal dimension, and can say it's in the X direction. And I'll make the vertical dimension B as such. And we're going to assume, and this would be in the Y direction, we're going to assume that the wave is propagating in the Z direction. So the net propagation effect is in the Z-axis, in the Z direction. It's being confined by this rectangular guide bouncing around. When we do this, we're going to also, when it says transverse magnetic, it means there's no magnetic field in the direction of propagation. So TM mode means HZ equals 0. That's what it means to you. If it was a TE mode, it would be EZ would be 0. Do you follow me on that? Transverse means that the electric field has no component in the direction of propagation. So TE would be the electric field would not have a Z component. TM, the magnetic field, would not have a Z component. Follow me, everyone?
Dr. Baginski?
Yeah.
I think you might have accidentally switched your camera to your computer screen.
Oh, got it. Sorry. My bad.
No worries.
Yeah, yell at me about that. I'm looking at you guys, and I should be looking there too. All right. So what I'm saying is I'm on page 388. I'm about to start equation 7.31, but I have to make the case. See how he has HZ equals 0 for TM? Transverse magnetic field has no Z component. That's it. This is TM. So when you do this, and we take a look at Maxwell's equations,
we can't see what you're writing.
I don't know what happened to my thing. Did that just shut up on me for no reason? I guess so. Let me try to blow that up a little bit. Maybe not. All right. Okay. So normally I would start with the two curl equations and get it down to 1, but right now I'm going to just tell you, I'll look at equation 7.31. This is what it comes down to. You're going to have a del squared of E minus, or he uses, sorry, plus beta unguided squared of E equals 0. Where this comes from is the two curl equations. We've done this before for plane wave propagation, and I think most of you remember something about that. Now, beta unguided is really equal to just omega times square root of mu epsilon, and this is inside the waveguide. So the waveguide could be filled with a material like a dielectric material, or it could be a pressurized gas or something, and it means mu and epsilon may not be mu 0 epsilon 0. But generally speaking, they're air-filled almost 99% of all waveguides, at least that I've worked around, have been air-filled. So this is the equation. Now, here's where the fun begins, and I'm not trying to bother you about this, but now I've got to go ahead and I got to get a solution for this, knowing, and I just want a solution for the EZ component, because I know there's going to be an EZ component, but there's not going to be an HC component. Do y'all follow me on that? When I do that, I have to use what's called separation of variables, and he does this in his book. This is a little irritating, but hang with me. So I can assume this, that EZ itself is going to be just a function of X times just the function of Y times just the function of Z. Y'all remember separation of variables in math, people? How many do? Anybody? Okay, Zach's. You should have been exposed to it. Separation of variables is very powerful. It's the first time around, it gets a little overwhelming, but it's very powerful and useful technique. And it doesn't always work. You can't always separate them. In this case, you can. Now, when we have the del square operator, remember, del squared in general is equal to second derivative with respect to x squared plus second derivative with respect to y squared plus second derivative with respect to z squared. And it's operating on this. So if you take a look at this, what's actually going to happen is, and he does this in his book, if I break this out, you get the second derivative of EZ with respect to x squared plus the second derivative of EZ with respect to y squared plus the second derivative of EZ with respect to z squared plus beta unguided squared EZ equals 0. Now I'm just going to substitute in, this is the irritating part. You don't have to write it down, just watch me. I'm going to go ahead and put these values in here, but I'm going to do it in the standard way that they abbreviated. You know, whenever you take a derivative, first derivative of something, they usually just put an apostrophe, and then two derivatives, two apostrophes. So when I take the second derivative of this function with respect to x squared, I get x double prime. So it's just x double prime times y times z plus x, and this would be y double prime z plus x times y times z double prime. Finally, it's beta unguided squared times x times y times z. And all this equals 0. Now, I'm just showing you what's in his book. But now I take this and I divide everything on both sides by the function x, y, and z. And when I do that, I get x double prime over x right here. And those are functions plus y double prime over y plus z double prime over z plus beta unguided squared equals 0. Just take a moment. Take a look what went on. I went ahead and I divided everything by x, y, and z. So now I have these functional forms left. And the reason I did it, you'll start appreciating this in a bit, but is the only possible way that this can be true for all values of x, y, and z is if this is a constant, if this is a constant, and if this is a constant. That beta unguided at a given frequency is a constant, beta unguided squared. So what they do normally here is, where's the book? I got to see what he does. Yeah, he calls it that. This, he'll say, is equal to just minus beta x squared. He'll call this one minus beta y squared, and this one minus beta z squared. Y'all with me on that? All right, so when I take a look at this equation just in x, I can see that I have, well, x double prime is the second derivative of x with respect to x squared, right? Divided by x, functional form of x, is equal to minus beta x squared, right? Just bear with me, it'll make sense. Remember, x itself is a function only of x, but we don't know what kind of function it is. So now I go ahead and I'll get the second derivative of x, that function with respect to x squared. And then it's going to be plus beta x squared times just the functional form of x equals 0. Now block that one or put a bracket around or something to make it stand out. Now that's a second order differential equation. X is representative of EZ. It's one multiplier on the possible solution of EZ. And this is a standard second order homogeneous differential equation. And it has possible solutions, can be either sine of beta x times x, or it could be a cosine of beta x times x, or it could be possibly e to the plus or minus j beta x times x. Any of these three could be the possible solution to this, and all three of them are solutions. Do y'all follow me on that? That's just a mathematical solution. But the actual solution agree with the boundary conditions of the problem. And if you read this, you'll see it's not. I'm going to go ahead and just turn this, okay, because I'm running out of paper here. And when you do that, you see this. When I look at the waveguide, and remember that E field I'm talking about is EZ, and this is 0, this has dimension A, and this is the X direction. This is 0, and this is dimension B, and that is the Y direction right there. And I have these possible solutions. Well, that's for EZ. I know one thing. I know that the value of EZ, because it's parallel to these boundaries, has to be 0 on all these surfaces. EZ has to go to 0 at the surfaces, at surface of a conductor. Do y'all follow me on that? That's E10 has got to be 0 on a conductor surface. That's just the rule. All right. Well, if you look at this, the cosine, when x is 0 right here, the cosine of 0 is 1. The cosine waveform can't do that. As a matter of fact, the only solution that makes sense is the sine. So that means the x variation will be equal to some magnitude, and you can just call it E naught x times the sine of beta x times x. Now that's going to be the form of the solution, but we're not quite done yet. I know I'm out of time. Let me just finish this thought here, and then I'll let you guys go. All right. Now that's going to be the form, and that one checks the box because when x is 0, right there, this goes to 0. The sine of 0 is 0. But it's also 0 when it's a. You all see that? When x is equal to a, EZ has to be 0. Now, when is a sine, the argument of a sine, make the sine 0? At 0, at pi, at 2 pi. Y'all follow me on this, guys? So you can say that beta x times this distance a has to be equal to, and call it m pi. Or now we have beta x. Beta x itself will be equal to m pi over a. And that is in his book. That's equation 7.39. I didn't get a chance to do it, but I'm going to show you this, and then I'll let you go. If you take a look right, I mean, we did it for x right here. We got beta x times a is m pi. I hope you can see that. Likewise, when you go ahead and solve for beta y, you basically solving for the y variation. It could be a sine or a cosine. It's going to end up being a sine because this is again something that's proportional to the EZ, and it's 0 at the boundaries. you're going to get beta y equals n pi over b. And then finally, we get beta, I usually call it beta z, but this is beta in the direction of propagation will be equal to this. Now, I didn't have time to really get into this the way I'd like to, but that's okay. What I'd like you to do is read through section 7.21 and don't get hung up with all this stuff here. This is all, don't worry about it. The real thing you have to appreciate is this right here, equation 7.42. That is the electric field in the z direction for a TM wave. And we'll pick that up on Wednesday right there, okay? Any questions? Sorry, I didn't have more time to do the entire development. Anything, guys? At all? Nothing? Thank you. All right, well, listen, have a safe weekend. Listen, if you guys
Hey
are
Doc, you still want me to bring these sunglasses on Wednesday?
yeah, bring them Wednesday, please. Bring both. Bring. If somebody else can bring a polarized,
I'll bring them all. We'll just see what happens.
yeah, we'll have fun. I think. Anyway,